My name is Jim Al-Khalili. I'm a professional physicist, and I've been making films about my passionate interest in science for many years. I never cease to be astonished at the awesome power of science in shedding light on everything in the universe, from the tiniest things in existence to extraordinary objects on a cosmological scale. In this series, I want to show you how science gives us insights into the biggest questions of all. How did the universe come into being? How did life start on Earth? And how does it sustain itself? What is the nature of space and time, the very reality we live in? And how will it all end? In this episode, I want to look at the astonishing amount that physics can now tell us about the natural world we see all around us. We'll investigate some deceptively simple laws of physics, which explain how life itself can exist and thrive in the universe. We'll learn how exquisite patterns of nature can emerge spontaneously from simple mathematical rules. I'll show you how my own research into the spooky world of quantum mechanics may help us understand some of the most important processes in life. And we'll tackle one of the biggest mysteries of all. How did life begin? I want to explore the latest developments and astonishing new theories that continue to shape the way we understand the universe. I hope this series will show you just how amazing our universe is. I'm going to start this episode by looking at one of the fundamental pillars of physics: the laws of thermodynamics. As unlikely as it sounds, it was steam engines which led to the discovery of these beautiful, simple laws. By the first half of the 19th century, steam technology was transforming human societies with bewildering speed. But although these engines clearly worked in practice, no one really understood the physics behind them. It took a brilliant French scientist working in the aftermath of the Napoleonic Wars to crack the problem. His name was Sadi Carnot. What really bothered Carnot was the technological superiority that France's enemies seemed to possess. So Carnot vowed to really try and understand how steam engines work and use that knowledge for the benefit of France. Carnot saw that all heat engines comprised of a hot source in cooler surroundings. Now, Carnot believed that heat was some kind of substance that would flow like water from the hot to the cool. And just like water falling from a height, the flow of heat could be tapped to do useful work. Carnot's crucial insight was to show that to make any heat engine more efficient, all you had to do was to increase the difference in temperature between the heat source and the cooler surroundings. Carnot had revealed that heat engines weren't just a clever invention. They were tapping into a deeper property of nature. They were exploiting the flow of energy between hot and cold. But as the 19th century progressed, the study of heat, motion, and energy began to grip the wider scientific community. Soon, it was realized that these ideas could do much more than simply explain how heat engines worked. These ideas were applicable on a much grander scale. By the mid-19th century, scientists and engineers had worked out very precisely how different forms of energy relate to each other. They measured how much of a particular kind of energy is needed to make a certain amount of a different kind. Let me give you an example. The amount of energy needed to heat 30 milliliters of water by 1 degree centigrade is the same as the amount of energy needed to lift this 12.5 kilogram weight by 1 meter. The deeper point here that people realized was that although mechanical work and heat may seem very different, they are in fact both facets of the same thing: energy. This idea would come to be known as the first law of thermodynamics. The first law reveals that energy is never created or destroyed. It just changes from one form to another. 19th century scientists realized this meant the total energy of the entire universe is actually fixed. Amazingly, there's a set amount of energy that just changes into many different forms. So, in a steam engine, energy isn't created. It's just changed from heat into mechanical work. But impressive though the first law is, it begged an enormous question. What exactly is going on when one form of energy changes into another? In fact, why does it do it at all? The answer would in part be found by German scientist Rudolf Clausius, and it would form the basis of what would become known as the Second Law of Thermodynamics. Clausius realized that not only was there a fixed amount of energy in the universe, but that the energy seemed to be following a very strict rule. Put simply, energy in the form of heat always moved in one particular direction. This insight of his is in fact one of the most important ideas in the whole of science. As Clausius put it, heat cannot of itself pass from a colder to a hotter body. This is a very intuitive idea. If left alone, this hot mug of tea will always cool down. What this means is that heat will pass from the hot mug, say, to my hand, and then again from my hand to my chest. This might seem completely obvious, but it was a crucial insight. The flow of heat was a one-way process that seemed to be built very fundamentally into the workings of the entire universe. Left alone, energy seems to always go from being concentrated to being dispersed. Clausius brought together all these ideas about how energy is transferred and put them into mathematical context. It could be summarized by this equation.
Now, what Clausius did was introduce a new quantity he called entropy, this letter S. Basically, what it's saying in the context of this equation is that as heat is transferred from hotter to colder bodies, entropy always increases.
It appeared to Clausius that in any isolated system, this process would be irreversible.
Clausius was so confident about his mathematics that he figured out that this irreversible process was going on out there in the wider cosmos. He speculated that the entropy of the entire universe had to be increasing towards a maximum, and that there was nothing we could do to avoid this. This idea became known as the Second Law of Thermodynamics.
The second law of thermodynamics seemed to say that all things that gave off heat were in some way connected together. All things that gave off heat were part of an irreversible process that was happening everywhere. A process of spreading out and dispersing. A process of increasing entropy. The second law says the universe itself must one day reach a point of maximum entropy, maximum disorder. The universe itself must one day die. If everything degrades, if everything becomes disordered, you might be wondering how it is that we exist. Contrary to what you might think, it's precisely because of the second law that all this exists. The great disordering of the cosmos gives rise to its complexity.
It's possible to harness this natural flow from order to disorder, to tap into the process and generate something new, to create new order, new structure. The engine of my car, like all engines, is designed to exploit the second law. It starts out with something nice and ordered, like this petrol, stuffed full of energy. But when it's ignited in the engine, it turns this compact liquid into a mixture of gases 2,000 times greater in volume, not to mention dumping heat and sound into the environment. It's turning order into disorder. What's so spectacularly clever about my car is that it can harness that dissipating energy. It can siphon off a small bit of it and use it for a more ordered process, like driving the pistons which turn the wheels. That's what engines do. They tap into that flow from order to disorder and do something useful. But it's not just cars. Evolution has designed our bodies to work thanks to the very same principle. If I eat this chocolate bar packed full of nice, ordered energy, my body processes it and turns it into more disordered energy, but powers itself off the proceeds.
Steam engines, power stations, life on Earth. All of these things harness the cosmic flow from order to disorder. But the laws of thermodynamics alone aren't enough to explain why there's so much complexity in our world, such intricate and apparently ordered structure. Ours is a world where inanimate matter spontaneously creates exquisite beauty, where a chaotic and unpredictable universe has turned simple dust into human beings. It's even more amazing when you consider that we ourselves are made up of just a handful of simple elements.
These are the elements and compounds from which all humans are made. They're incredibly, almost embarrassingly common. In fact, almost 99% of the human body is a mixture of air, water, coal, and chalk, with traces of other slightly more exotic elements like iron, zinc, phosphorus, and sulfur.
In fact, I've estimated that the elements which make up the average human cost at most a few pounds. But somehow, trillions of these very ordinary atoms conspire miraculously to organize themselves into thinking, breathing, living human beings. How the wonders of creation are assembled from such simple building blocks is surely the most intriguing question we can ask.
The answer lies in the extraordinary world of chaos theory. Before the coming of chaos theory, scientists had a pretty fixed idea of how everything in the universe worked.
In essence, by the beginning of the 20th century, scientists saw the universe as a giant, complicated mechanical device. Kind of a supersized version of this orrery. The idea was that the universe is a huge and intricate machine that obeys orderly mathematical rules. If you knew the rules of how the machine was configured to start with, as you turn the handle over and over again, it will behave in an entirely predictable way. If a nice mathematical system that worked in a similar way to my orrery, scientists assumed some malign outside force was causing it. The man who forced the scientific community to confront it was an American meteorologist called Edward Lorenz. In the early 1960s, he tried to find mathematical equations that could help predict the weather. Like all his contemporaries, he believed that in principle, the weather system was no different to my orrery. A mechanical system that could be described and predicted mathematically. But he was wrong. When Lorenz wrote down what looked like perfectly simple mathematical equations to describe the movement of air currents, they didn't do what they were supposed to. They made no useful predictions whatsoever. It was as if the lightest breath of wind one day could make the difference a month later between a snowstorm and a perfectly sunny day. How can a simple system that works in the regular clockwork manner of my orrery become unpredictable? It's all down to how it's configured, how the gears are connected. In essence, under certain circumstances, the tiniest difference in the starting positions of the cogs, differences that are too small to measure, can get bigger and bigger with each turn of the handle. With each step in the process, the system then moves further and further away from where you thought it was going. Lorenz captured this radical idea in an influential talk he gave called "Does the Flap of a Butterfly's Wings in Brazil Set Off a Tornado in Texas?" It was a powerful and evocative image, and within months, a new phrase had entered our language, the butterfly effect. It seemed unpredictability was hardwired into every aspect of the world we live in. The global climate could dramatically change in the course of a few short years. The stock market could crash without warning. We could be wiped from the face of the planet overnight, and there is nothing anyone could do about it.
Scientists realized that there was an unexpected link between nature's power to self-organize and the chaotic consequences of the butterfly effect. Complex and unpredictable natural systems can emerge from surprisingly simple mathematical rules. These rules have a unique property, often referred to as feedback. This screen behind me is connected up to the camera that's filming me. But the camera in turn is filming me with the screen. This creates a loop with multiple copies of me appearing on the screen.
This is a classic example of a feedback loop. We get a picture in a picture in a picture. At first it seems fairly predictable, but as we zoom the camera in, some pretty strange things begin to happen. The first thing I notice is that the object I'm filming stops bearing much resemblance to what now appears on the screen. Small changes in the movement of the match become rapidly amplified as they loop round from the camera to the screen and back to the camera. So even though I can describe each step in the process mathematically, I still have no way of predicting how tiny changes in the flickering of the flame will end up in the final image. This is the butterfly effect in action. But now here comes the spooky bit. With just a slight tweak to the system, these strange and rather beautiful patterns begin to emerge. The same system, one that's based on simple rules with feedback, produces chaos and order. But one scientist, more than any other, brought a fundamentally new understanding to this astonishing and often puzzling idea. His name is Benoit Mandelbrot. Underlying nearly all the shapes in the natural world is a mathematical principle known as self-similarity. This describes anything in which the same shape is repeated over and over again at smaller and smaller scales. A great example are the branches of trees. They fork and fork again, repeating that simple process over and over at smaller and smaller scales. The same branching principle applies in the structure of our lungs and the way our blood vessels are distributed throughout our bodies. It even describes how rivers split into ever smaller streams. And nature can repeat all sorts of shapes in this way. Look at this Romanesco broccoli. Its overall structure is made up of a series of repeating cones at smaller and smaller scales. Mandelbrot realized self-similarity was the basis of an entirely new kind of geometry, and he even gave it a name: fractal.
What I'm about to show you is one of the most remarkable mathematical images ever discovered. Epic doesn't really do it justice. This is the Mandelbrot set. It's been called the thumbprint of God. And when we begin to explore it, you'll understand why.
Just as with the tree or the broccoli, the closer you study this picture, the more detail you see. Each shape within the set contains an infinite number of smaller shapes, baby Mandelbrots that go on forever. Yet all this complexity stems from just one incredibly simple equation. This equation has a very important property. It feeds back on itself. Like a video loop, each output becomes the input for the next go. This feedback means that an incredibly simple mathematical equation can produce a picture of infinite complexity. The really fascinating thing is that the Mandelbrot set isn't just a bizarre mathematical quirk. Its fractal property of being similar at all scales mirrors a fundamental ordering principle in nature. Complex systems can be based on simple rules. That's the big revelation. Design does not need an active, interfering designer. It's an inherent part of the universe.
So we've seen how two of the major pillars of physics, thermodynamics and chaos theory, explain so much about the structures of life and the basic laws that underpin it. But in recent years, and this is an area I've personally become involved in my research, it's been realized that quantum mechanics may also play a role in explaining some of the most important mechanisms of life.
As we saw in the previous episode, the behavior of subatomic particles is completely baffling. They behave as though they're smeared out in space. They pop in and out of existence all the time. And you can only express their location and movement in terms of probabilities, not certainties. But for decades, no one had any idea that the Alice in Wonderland world of quantum mechanics could be important in the realm of biology. In recent years, that's changed. Quantum biology is a growing branch of science. And at the University of Surrey, my colleagues and I are heavily involved in pushing back its boundaries. We think spooky quantum effects may play an important role within living organisms. I'd like to show you an example, a bizarre process called quantum tunneling. When physicists say you have to put in effort to get something done, we have a special term for it. We say you have to overcome an energy barrier. I want to look at quantum tunneling because it's an extraordinary way in which particles can move, enabling them to cross energy barriers, barriers which are even more challenging than the walls of a medieval castle. It all revolves around another strange fact from the world of quantum mechanics. Particles can cross barriers in a very spooky way indeed. They act like ghosts.
I wouldn't blame you for thinking that this is an idea that a clever theoretician has come up with, that it's just mere speculation, something that we have no proof of. But we do. It takes place all the time.
In the quantum world, protons don't have to go over barriers. They can tunnel straight through.
A quantum particle can tunnel from one place to another, even if it has to pass through an impenetrable barrier.
In nuclear physics, this effect is a proven fact. The most important advantage of tunneling is its speed. It happens incredibly quickly, much faster than if protons go over the barrier.
As a nuclear physicist, quantum tunneling is my bread and butter. Subatomic particles like protons do it all the time. But what has this got to do with biology?
At the University of Surrey, we're currently researching whether quantum tunneling is involved in the central process which propagates and diversifies life on Earth.
You'll probably recognize this as the famous DNA double helix, discovered by Crick and Watson in 1953. This molecule contains our genetic code. It's the instruction manual for all life on Earth. The double helix structure is stable. It's like a twisted double spine, like a twisted ladder. But it's the rungs of the ladder that are of interest to me. They're made up of 4 smaller molecules called bases: adenine, thymine, guanine, and cytosine. And these bases fit together in a very special way, like pieces of a jigsaw puzzle. So the 2 strands fit together when guanine fits to cytosine and adenine fits to thymine. But every now and again, mistakes take place, and understanding how and why they happen is incredibly important.
The evolution of all living things depends on DNA mistakes, known as genetic mutations. Sometimes a mutation might give an organism an edge in their environment, and they can reproduce more efficiently over very long timescales. That's how species change. But how do these mutations occur? Let me take you through a hypothesis we're currently researching.
Here's a computer simulation produced by my PhD student, Max. In the foreground, you can see the DNA double helix in color, and the gray blob in the background is the helicase. Now, that's an enzyme that splits the 2 strands of DNA apart so that each can then make a copy of itself. Now, if we zoom in, we can see the bases all linked together inside the DNA, but we get into the business end. So down at the molecular, at the atomic level, the green is guanine and the yellow is cytosine. These 2 bases that are held together by hydrogen bonds like this one, which is basically a proton. So now we're down at the quantum realm, which of course is my specialism.
It's this subatomic bonding of the bases which most interests me.
Now, these protons spend most of their time on one side, but every now and again they can jump across to the other side. However, they just jump back again. But if the 2 bases split with the protons in the wrong positions, then that changes the shape of the bases. Now, when the strands of DNA make copies of each other, green would normally fit with yellow. However, now they can't. They're like jigsaw pieces that don't fit together. But if an orange comes along, green can fit to it. However, this shouldn't happen. Green shouldn't fit with orange. This is a mistake.
Now, of course, you can guess how we think the protons jump. We think quantum tunneling is happening inside DNA. Which means it could be one cause of mutations. I'm working on this theory with Professor John Joe McFadden.
Mutation can be caused by many different phenomena. Radiation causes mutation. Ultraviolet light causes mutation. So there are many mechanisms of causing mutation, of which the proton moving from one place to another is one of them.
If it is the moving proton that causes mutations, it could find its way across the energy barrier, not by quantum effects, but what we'd call ordinary Newtonian physics.
The question is whether they move by classical ways, like a snooker ball moving from one place to another, or whether they move by quantum mechanical means in which they essentially disappear from one position and appear at another.
Our preliminary results look very promising.
The recent work of our students then has revealed if it moves at all, it moves quantum mechanically. If the proton moves from one place to another, it's doing it as a quantum mechanical particle.
It's possible this might even have far-reaching consequences in the medical world too.
And of course, mutation is responsible for evolution, but it also has a bad side. It's responsible also for making cancer cells cancerous. Cancer is caused by mutations. Single molecules have macroscopic effects. They change us. And mutations in single molecules can mean the difference between life and death.
It's very exciting to me to think that the great pillars of physics, thermodynamics, chaos theory, even quantum mechanics, are being used to help us understand the ordinary natural world around us.
Now I want to end this film by looking at one of the greatest mysteries in all of science. How did life itself begin?
Let's think ourselves back, perhaps 4 billion years, to a primeval Earth, with simple chemicals in a rock pool and energy flowing in from a thermal vent. It's one of the great outstanding mysteries of science. How did simple chemicals become the complex forms we know as life? It's not often realized that the underlying principles of life come from the laws of physics, such as thermodynamics. I can even show you the basic principles in action with a simple little backyard experiment.
Now, all I've got in this pan is some silicon oil. There's a bit of mica powder in there, but that's just to add color. A physicist or chemist would say that until I put it on the stove, there's no energy going in or out. And of course, it has no structure to it. But as soon as I heat it up, hopefully some interesting things will happen.
Quite rapidly, these shapes appear. They're known as convection cells. They formed because the bottom of the oil has suddenly become very hot. The system has lots of new energy pouring into it. And as the heat dissipates through the system, ordered symmetrical structures spontaneously appear.
These pretty convection cells are a classic example of something we see again and again in the physical world. They're called dissipative structures.
It's worth remembering that this isn't a chemical reaction. All that's happening to this oil is that heat, energy, has been pumped into it. Some scientists think understanding the flow of heat through dissipative structures is key in understanding the development of life. Recently, an experiment was carried out by a team of scientists in America using these little robots called smarticles. Switch their batteries on and all they can do is flap their arms about. So generally they just crash about randomly. It's all a bit of a mess. They're acting individually, and the whole system is chaotic and unstable. But then the scientists programmed these smarticles to move their arms in a more predictable up and down way. Quite quickly, this collective behavior spontaneously emerged, almost like synchronized swimming. These smarticles look like they've been choreographed, yet they haven't been programmed to join up or to cooperate in any way. They just self-organize into regular patterns, even leading each other in a little orbit around the ring. The scientists realized the smarticles were somehow choosing the structures which would enable them to stay stable and avoid being knocked around by the patterns of energy flowing through the system.
They discover these dances, these kind of organized collective behaviors, because this is the way that they can work together so that the energy flowing through them doesn't disorder them and just kind of maintains them in that state.
So the idea being explored is that on a primeval Earth, chemicals encountering a predictable source of heat may have entered a feedback loop, changing their shape to become more stable as the energy flowed through them.
One of the properties of living things is that they are able to maintain themselves in this specialized state only because the energy flowing through them has a very particular pattern to it, and that they've kind of adapted or emerged even in the presence of that kind of pattern. So it's an evolutionary process then.
In effect, it's a kind of natural selection process, favoring the combinations of chemicals that find the most stable form. Ideas like this may help us fill in a huge gap in our understanding of how life developed.
I think that sometimes people have a tendency to kind of imagine that before there's life, you just have random mess, and that you need a completely unimaginably unlikely coalescence of recognizable lifelike structure out of absolute vacuum, so to speak, out of nothing that looks like that at all. And this is about how I think the physics helps you to maybe fill in a gray spectrum between that extreme inchoateness on the one hand and something that you'd call life on the other, where in between there's a lot of lifelike emergence that you can argue for.
So could it be that the physical laws of the universe actually make life more likely than we've previously imagined? It's clear that science is starting to get to grips with some of the greatest mysteries of life.
Here's a philosophical question for you. Where do you draw the line between life and non-life? I think we can all agree that fire isn't alive, and yet it has a lot in common with life. It needs energy, heat, to survive by burning fuel in the same way that we burn calories. It can create beautiful transient patterns, and it has the ability to reproduce itself.
So at what point did non-life become life? At the University of Glasgow, a major project is underway to try to actually create life in a lab. Professor Lee Cronin and his team have built a series of chemical computers called chemputers. This is Genesis engine number 1, Genesis engine number 2, and there's a series of other origin of life machines. The machines are designed to gather together the simplest molecules which might have been found in a rock pool on a primeval Earth, such as carbon dioxide and methane, adding methanol and water, and then driving heat through them. Then the scientists study the molecules as they combine and recombine through cycle after cycle.
Now, what are we looking for? We're looking at molecules that are growing, getting bigger, molecules that are related to one another. Maybe they have the same, almost the same identity, but a bit different. And because then that would be what we see when we see evolution starting, as the molecule parent makes a slightly different child, but you can see that they're related and they carry on going.
Lee believes any theory of life has to be based on information, because at the most fundamental level, it's information that describes complex systems and which is necessary for things to evolve and change.
Probably life didn't really emerge in chemistry, it emerged in information, and chemistry just happened to be the substrate that carried it.
He's working closely on this idea with theoretical physicist Professor Sarah Walker.
So I'm working with Lee on some of these ideas because I had this kind of drive to develop a theory for what life is, which is really based on this concept that somehow information is going to be playing a critical role in what we might call the physics underlying life. Objects like you and me, the cup, the Zoom, complex molecules like proteins and things, all of those things require information or an evolutionary process to create them in the universe, and that's the physics we want to understand. How does the universe spontaneously generate information and information processing systems that then undergo this process that we call evolution and build all the complexity that we see in the world?
This is thinking on the grand scale, not just the origin of life on Earth, but everywhere in the universe.
My mission in science is to basically come up with the plausible scenarios that would give rise to the origin of life on Earth. But actually, who cares about that? It's like saying we want to understand the origin of our sun. But when you look in the sky, there's suns everywhere. So what I want to do, if this works, I'm not going to work out what did happen. I'm going to be able to work out what does happen. My very strong belief, it is a belief, and but what I'm trying to do is test this belief, is that life is everywhere. So by understanding the origin of life and making life now, we will be able to statistically map how life works in the universe.
One of the reasons physics hasn't been able to explain life yet are concepts of what the theories need to look like are just not structured properly yet. And we haven't been creative enough to think about breaking free of the mold of physics as it's been done in the last 300 years and invent new ways of doing it to address the problems that are in front of us now, like what is life? What are minds and consciousness? How does intelligence evolve over planetary scale timescales? What other things like us might exist in the universe?
Right now, life on Earth means nothing if Earth gets obliterated and we don't affect the rest of the universe. So my ambitions, Nobel Prize, that's too low an ambition. The ambition is to create a technology that we could seed the universe to transmit our origin of life idea and create other living worlds where there weren't none. And I can imagine us having an ethical debate in the future when we know how to do this, to say, is it ethical to infect this planet with an origin of life scenario? Are we going to destroy the life that's on the planet? Is the planet definitely dead? So my ambition is to make sure that we find life elsewhere in the universe, understand life on Earth, and if there's not life elsewhere in the universe, we better make sure that we make the most of our universe by making sure life escapes Earth.
As we've seen throughout this series, today's generation of scientists are pushing back the boundaries of what it's possible for us to know at a breathtaking rate. I believe that as a human race, we should take pride in our achievements, that science is at the threshold of answering the deepest questions of existence. And for me, physics is the true path to understanding the nature of reality. And with that understanding, we can shape our world and our destiny.